Okay, Dr. Meng, I think we can start now. Wait, Dr. Meng, I think you're muted.
All right, so let's get started. Hello, everyone. Good evening. I'm very glad to open this session. This Young and the Young Machine Learning uh, for AI workshop. Okay. Hi again. I'm Dr. Meng. I'm the founder and executive director of Arcogene Technology Academy. I describe myself as a technologist, a innovation coach, and a blog writer. So it's a great pleasure to welcome all of you to this 5-day Young and Young Machine Learning for AI workshop. We are living through one of the most profound technological changes in the human history, as you are aware. AI, artificial intelligence, is already changing how we learn, work, communicate, create, and solve problems. In the future, avoid AI may not be almost as difficult as avoiding internet, smartphones, modern transportation today. So avoid learning AI is not an option. So that means learning AI is a must now. AI can greatly expand our ability, just like a machine increased human physical strength and a computer increased our ability to calculate. And artificial intelligence can help us to, do a lot of things. Analyze information, write program, generate ideas, and complete tasks much more efficiently. However, note, greater productivity does not automatically create a great competitiveness. So when everyone has access to powerful AI tools, the real difference between you and others, your competitors, will come you use them. Successful students will not simply ask questions, ask AI to work for you. To do your work. The students should definitely evaluate answers, make decisions, and use AI to solve meaningful problems. In the future, intelligence will increasingly become a partnership between humans and machines. Human begins uh, Human beings must provide creativity, judgment, purpose, responsibility, and value. While AI can provide like a speed, information, analysis, and technical support. So for this reason, learning AI is no longer simply an optional interest. It's becoming an essential skills for everyone. Okay, so that's why I am especially pleased to introduce these two. I would like to introduce two distinguished instructors of this workshop, Victor and Forrest. Both are members of the United States Artificial Intelligence Olympiad National Training Camp. And also they achieve many, they have many, many outstanding achievements, including researchers in if I remembered it right, biology and psychology, education, and some other areas. So their experience, what is the inspiration from their experience? Their experience represent an important direction for the future, which is we must learn two things at the same time, AI plus domains. Okay, so And previously, you probably get a major in some subjects like physics, engineering, biology. Now, again, I want to say AI plus domains will combine artificial intelligence with other fields, such as medicine, biology, engineering, education, psychology, you name it, finance, and even the arts. So, and use technology to solve real world problem. Again, real world problem. Okay. So Victor and Forrest have volunteered their time during summer break to organize this completely free workshop for, middle and high school students. I appreciate their efforts because I know this not only benefit, this is not an action benefit themselves, but it's benefit everyone, our society. So that is important. Okay, this is associated with their research, the purpose of research, and their contribution, to solve real will be benefit others, not just construct some toy for yourself. Yeah, I also want to welcome and congratulate everyone in this workshop to attending the workshop. By joining the workshop, you have chosen to invest your summer evenings in learning and challenging yourself. You are not only simply attending several classes, you're opening a door to new opportunities and take an important step towards the future. So thank you again, Victor and Forrest, for your leadership and your services. Thank you for for your parents and some volunteers and all these supporting organizations. I want to appreciate you guys to make this happen. More importantly, thank you every student for accepting this challenge and taking an important step towards the future. So without further ado, I'll hand over the time to Victor and Forrest. Please give them a thumb up in the chat.
Okay, thank you everyone. And thank you, Dr. Meng, for giving such a great introduction. Okay, I will share my screen now. And if you have any questions, please feel free to unmute. And if you do not want to unmute, you can also ask in the chat where I will respond. Yeah. Okay, so I will leave these slides up during the break so that if you have not joined the Slack or if you have not created a Google Colab account, we can talk about that in the break. I'll leave this up. Okay. So everybody, you can open the notes, and I think I've sent everyone the notes in Slack and through email. Okay. And if you want to just take notes on a separate piece of paper, that's fine, or you can write on the PDF, that's also fine. Okay, we can get started. So for machine learning, machine learning is a very broad topic. Inside there's deep learning, but we're going to talk about traditional machine learning for this workshop. And there will be 3 types. The first is supervised learning, the second is unsupervised learning, and the last is semi-supervised learning. So let's look at supervised first. So in supervised, we have 2 phases. It's called training and inference, or prediction. So for training, we have our data right here, X. What we want to do is we want to learn a function, we want to learn a mapping to get a prediction of the Y. So let's say X is here and Y. We want to learn a mapping, a function. And the function is parameterized by theta. And we'll talk about what the theta exactly is. We'll show an example because later we'll look at linear regression. So what do we do during training? Well, there are many functions and there are many possible parameter values, right? So we want to find the best parameter value that minimizes a loss function between our prediction and the real y, or the real value. like the ground truth value. So here we have this word, do not be scared by the notation, is argmin. It is like the argument min. So basically we want to find the theta in a set, and this is like the set of all possible thetas. And that's usually just all real numbers. So we want to find the theta that minimizes this loss function. So that's why it's the argument, because right now it is an argument, it's a parameter. If I just said min, then that would be what is the minimum loss. So I just want to kind of differentiate that. Okay. So now what happens after we find the best theta? Then we'll do inference. Inference, we try to predict on a test set, on this test that we've never seen before. So we've never seen this X test before. We directly predict, and you can see we're using the learned best parameter here, and we try to predict the Y test. So that is supervised learning. That's the most common form and the most like typical form of machine learning. So right here, F is parameterized by learnable theta, and F is a predetermined model. So for example, there are many models like linear regression, logistic regression, which we'll talk about today, neural network, trees, etc., transformer. So F can be any function, and F will have many parameters. And F is also modulated by non-learnable preset hyperparameters. And we'll talk about that more in the second class, like how we tune hyperparameters, etc. So hyperparameters might be like the learning rate. We'll have a set learning rate when we try to find the best parameter theta. So the learning rate will not change. But after we find the best theta, if we think, oh, let's try another learning rate and see if we can get a better model, so that would be called hyperparameter tuning. Okay, now let's continue. So now let's look at unsupervised learning. So unsupervised learning is we do not have, we may not have the Y train right here, but we actually may have it. I'll talk about what we can do if we have it. So for the training phase, what are we going to predict? We're going to predict the X. So an example is like image generation. We have an image. We try to duplicate, we try to replicate another image, and we try to make these two images very similar. So that is exactly what unsupervised learning is. You can see it's the same thing. We still have our model, it's still parameterized by theta, and we still try to find the best parameters. And the theta can be in any of the big set theta. And we try to find the best argument, best parameter theta that minimizes a loss function. And now you can see it's between X string and our predicted X. And during inference, it's the same thing. We will use our best model right here to replicate the X on a test set that we've never seen before. Okay, so now let's talk about a few examples of what this may look like. So first, clustering methods. For example, k-means. So let's say the data looks like this. There are many, there's a cluster right here, and there's a cluster right here. Well, these are all X. These are like this may be a feature and this may be another feature. There is no Y in here. There's no ground truth value in here. So, and do you need a ground truth value to find that there are two clusters in this graph right now? No. So that is k-means. But if we have the ground truth Y, what can we do? Well, we can say that, oh, I noticed that most of these are, let's say, people who have a disease. So yes, disease. And these most have the label of no. So then can I turn this unsupervised learning into supervised? Or like, can I turn it into supervised inference? Yes, you can say, oh, I have a new point. It is right here, this new point right here, this blue point. Well, it is close to the yes cluster, so I'm going to predict that this person has the disease. So that is how we use clustering. Next, we have dimensionality reduction, and some famous examples are PCA and UMAP. And we'll talk more about that in the third class. So I'm not gonna, because right now we're kind of the introduction took a little bit long. Okay, and then next is the image generation, like I said. So let me draw us a better graph, a better figure for the image generation. So for image generation, let me just switch over, okay, to here. So for image generation, we may have an image like this, and then we down project it to a latent vector, like a latent representation. And then we will up project it back into our predicted image. So this is what most image generation looks like. So this is down project, and this is up project, and this is our latent vector. And this basically contains information on what does this image look like. For example, if this image is like a person, then the latent vector might have, for example, what's the hair color? What is the facial expression? And it has different values. Okay, but we'll talk about more ML models uh in the third class. Okay, and finally, let's look at semi-supervised learning, which is a small amount, a small number of samples have labels, but the majority or the rest do not. And you may ask, well, how did that happen? Well, maybe there are too many data and it's just too hard to label them all. Like for example, if you like look into astronomy, there might be like huge amount of data, but it's too hard to manually label them all. So what can we do? Well, first, there are some existing methods. First, we can have a distance equals similarity method. So that's very similar to the k-means algorithm right here. So it's the same thing. Like if a point right here, like this purple point, is close to the second cluster, then I'm gonna predict that this point is null. So that's the same thing. And pseudo labeling, we'll talk about that more in the third class, but pseudo labeling is basically like this. So right now we have our label data and we have our unlabeled data. Let's say it's looking like this. And the label data, let's make it red, and the unlabeled data, let's make it blue. Okay, so then what pseudo labeling does is we train on the red part first, because that's the part that actually has the label. Then we predict on the blue part. For the blue part, if the prediction is very confident, for example, we can define a score and a threshold. If the prediction confidence is more than 0.9, let's say, then we will put that into our training set and expand our training set like that. So that we can have more training samples. And then we retrain and then repredict and then do this iteratively. So that in the end, we may get a lot. Most of this is actually being trained on. So that is really good. Okay, now let's move on to the topic of regression. So what is regression? Regression is we're going to talk about this is all supervised learning, by the way. Okay, regression, the why, the ground truth, the thing that we're trying to predict is continuous. So for example, income, like $2.99999, height, or like for example, 1.3456 meters, temperature. So all of these can have infinite decimals. It is continuous. It is not categorical. Okay, now here is the training. So let's represent the training data set like this. So I will explain about matrix vector and matrix multiplication later. It is very intuitive, but I'm right now I'm just gonna represent the training data set as we have X and we have Y. That's it. So, and this notation means we have many samples. We have n samples. So basically, for each sample we have X and Y, and I'm stacking this from n equals 0 to n big N minus 1. There's no question, right? Okay. Now, let's look at a few loss functions. Like up here, we have said we have to have a loss function to determine what theta is the best. So what are some common loss functions for regression? Well, the first one is MSE, mean squared error. It is right here. So let's look at this formula. First, this is saying we take in the real ground truth training Y and our predicted Y on the train set. So we take them in. And what do we output? We output a scalar, a number that is more than zero, more than or equal to zero. And what is the formula? The formula is simply each y minus our predicted y, and then squared. And then we sum all of that, and then we take the mean just by dividing by n. That's it. So, and why is this good? Because the squared right here, that makes sure that if the ground truth, like this subtraction might be negative or it might be positive, but our error should always be positive. Like if you are more than the ground truth or you're less than the ground truth, that should count the same. So that's why we do a squared, because we all know that squaring makes everything positive, right? Okay. And now here is a notation in vector form. And let me just say what that is. So here we can put all of these ny's into a vector, right? We can put them as y0, y1, and then yn minus 1. And then we can also have a separate, the same thing, but we have the our prediction. So I'm not gonna write it all. Okay. So what is this? What does this notation mean? This basically means we just minus these two vectors, and we all know that when we minus vectors, it is element wise, right? So we minus them, so it'll be this minus this, and then this notation is called the L2 norm. What that does is the same thing that this does. It is just we will take the square and then sum them all, and then we divide by n right here. Okay, and you can see that because we're taking the sum, the end product is just a number that's greater or equal to zero. So that is the mean squared error. And makes sense, right? Error cannot be less than zero. That does not really make sense. Okay, and some things about this is that MSE is smooth and it will provide decreasing gradients. And we'll talk about that later, very soon. And however, it is sensitive to outliers. Okay, let's move on. The next is MAE, is mean absolute error. And you can see it's very similar. All we're doing is we want to get the absolute value. So that's like very similar to the square, right? We just want everything to be positive. But there are many ways for things to be positive. For example, this absolute value function or the squared function. So that's just a different just a different type of error, and we call that mean absolute error. Okay, so in the vector notation, these two bars with the subscript 1 is the L1 norm. And that does the exact same thing as this. Okay. So finally, of course, it is also greater or equal to 0. And we'll talk about the gradient later. So for MAE, the gradient has constant magnitude because we all know the absolute value function is like this, right? So if you have learned AP calculus, you know that this is just a line. So the gradient has constant magnitude, so it does not smoothly approach 0 near the optimum. And that's why MAE is not usually used as a loss function. However, it is definitely less sensitive to outliers. Okay, now let's move on to linear regression. So here I'll talk about a lot of the vector notation. Like for the above, if you did not fully understand, that's fine. I'll talk about the vector notation very in detail now. Okay, so first, let's let's say we want to predict a house's market value based on the land area, the distance to the nearest school, and the average neighborhood annual income. So you can see that the market value, that is a continuous variable, right? The land area is a continuous variable. The distance is a continuous variable, and the average neighborhood is a continuous, the income is a continuous variable. So the x and the y are both continuous. They're both just scalars. They're both just numbers. Okay, and you can see that each sample can have many features, right? So in this case, we have three features: the area, the distance, and the income. So let's define a feature vector. Let's find a training sample feature vector right here. And vectors and matrices, they're just ways of storing information. They're not anything that is super complicated. So you can see that right here, I'm just storing. So the superscript n means we're looking at one sample. So for each sample, I have d features. That's it. So this might be land area. This might be distance. And this might be income. That's it. So that is the x vector. And that is with a superscript n. That means that for the nth sample. So, and this notation right here is saying that this is a vector with dimension d. That's it. And each individual value is a real number. So that is very easy, right? Okay. So I'm basically, so what I'm doing is I'm just storing the values in the vector. That's all I'm doing. Okay. Now let's continue. So that was a vector for each sample. Can we combine that into a big feature matrix? Yes. So the big feature matrix is a big X. And the transpose right here. So a vector is always like this. It has many values. So the shape is d by 1. So there are d rows and just one column. And the transpose means we're going to just turn it around. That's it. That's all the transpose means. So what I'm doing here is I'm turning each x horizontally. I'm laying it flat. And then I'm going to stack them all like this into a big x vector. So what that basically is, so this big matrix will have n rows, and each row is a different sample. And each column is a different feature. So this will be x0, 0, x1, 0, x2, 0. And then this next row will have x0 down here, but it is the first sample now. I mean, it is a sample of index 1. And then x1, 1. And then x2, 1. So that is all we're saying. We're just storing all information in a big matrix. That is it. And what does this mean? This means that we have, oh, okay, let me increase the screen. This means that we have n rows and d columns, and every value is a real number. It's a scalar. Okay. Now let's move on. So what is the linear regression model? The linear regression model is simply a linear combination of features, or you can say it's a weighted sum. So we're going to predict each sample's y with a bias term and these individual weights. So the theta 1, theta 2, theta d, those are all weights, and they're all learnable. So basically, learnable means what should those theta be? What should those thetas be? And above, I've talked about that for supervised learning, we're trying to find the best thetas, right? So this is what I mean by like linear combination and supervised learning. Okay, so basically, we just look at each x, each feature. Each feature gets its own weight. We have a sum and we have a bias and we predict the y. That's it. Now, notice, what can I do? Can I say this theta 0, can I expand that to theta 0 times 1, right? I can expand that. So then let me define, so first let me define the theta vector right here. I'm just putting the d scalars into a vector. That's all I'm doing. I'm just storing them in a vector. And you can see that it is d plus 1 because we have the bias right here. And then these are for the d features. So that's why it's d plus 1. So right here, you can see that all I'm doing is timesing by 1, and I can always do that, right? So what if I added a 1 to every vector? Every of our training vectors, and let me call that to be x bar. Let me rename the vector to be x bar. So I've just added a 1 here. And now, of course, the shape is now d plus 1. Okay? And I'll talk about why we do that. Next, because we did this, our big uh, feature matrix, our big training feature matrix will change as well. So it is the same, we stack them all, but because we've added the 1, can I say the ones are all right here? There's a 1, there's a 1, there's a 1, and there's a 1, right? So above, like this big matrix, what we did is we just added a 1, 1, 1, 1. So now the shape is n by d plus 1, right? And what we did is we just appended a column of 1s to the left of x, right? Just like what I said right here. Okay. Now let's continue to look at, so now we've did all of the x and the theta. Can we put the y's in the vector as well? Yes. Let's do that. So this is just the 0th sample, the y, the first sample, the y, and the n minus 1th sample, the y. So the shape is n. So we're also just, this is just storing everything in a vector. There's no complex math yet. Okay. So finally, can we use this vector notation to write this linear combination equation right here? So now I need to introduce to you matrix multiplication. So let me see. Let me use the eraser right here. Okay, I'll do a brief example of how matrix multiplication works. And then I'll try to make it clear so that you can easily see how we turn the linear regression, the linear combination formula into a matrix multiplication. Okay, so this is what matrix multiplication is. It's very simple. Let's say we have 1, 0, 1, 0, 2, 1, 3, 0, and 4, 1, 2, 1. And this shape is 3 by 4, right? And let's have another matrix. It is 0, 1, 1, 2, 3, 0, 2, 1. So this shape is 4 by 2. So matrix multiplication, when we have two matrices, the first one has to be A by B, the shape. The second one has to be B by C. So these two must be the same, and you can see why later. And our final shape will be A by C. So how does it work? Well, it's very simple. It is just this term times this term plus this times this plus this times this plus this times this. And that will be our first value, which is 3, right? Okay. Now, the final shape should be 3 by 2, given by this formula right here. So we should have a value here, value here, value here, and a value here. Now, what is the value for this one? Well, it is just this times this times this. Oh, and sum all of these, plus this times this, plus this times this. So what is that? That is 1. And then when we go to the next row, we just simply go to the next row here. So this times this, plus this times this, plus this times this, plus this times this. So that will equal 10, right? Okay, so that is basically matrix multiplication, and we do not have a lot of time, so I will go a little bit quicker. So a special case is the dot product. The dot product is just if I have a matrix of size 1 by n, or let's say 1 by m, and I have a matrix right here. Its size is m by 1. So when I multiply these, what do I get? I get 1 by 1. And it is just this times this plus this times this plus this times this, right? So, and what does that exactly look like? That exactly looks like our linear combination right here, right? This times this plus this times this plus this times this. Okay, so let's write everything into a matrix format. So first, let's look at this. So my theta is theta 0, theta 1, theta 2, and the x right here is like this. So it is x0 of n, x1 of n, and xd of n. And we know that this one, we just changed it to 1, right? We just appended the 1, so that is 1, and this is the bias. So this is basically the dot product. The linear combination is just the dot product of these, right? So that is why this formula makes sense. And then next, I want that's only for one y. And what if I want to predict all of the y's? And I previously said we stack all of the y's like this, right? So if I want to predict all of the y's, all I need to do is a big matrix multiplication. So now here is theta 0, theta 1, theta d. This big X is what I said previously, is each row, right? So basically, we put this into the row here. And the next row is, so this one is n equals 0. This row is n equals 1. And this row is n equals 2, and then etc. So I said matrix multiplication is this times this plus this times this plus this times etc., right? So this first matrix multiplication gives me my first y value. And this second row with this will give me the second y value. And then we keep on going. So you should now understand how this works. And if you do not understand, you can look at it later. But you can always use your own time to like think about like the multiplication. But it should be very easy if you understand how I just explained matrix multiplication right here. Okay, now let's talk about gradient descent. That is the main focus of today. So let's say we have a function. The function is let's say we have a function parameterized by x, y, z, etc. So here, so let's talk about what the gradient is. The gradient is also a derivative. So let's talk about what derivative is. So let me use this page down here. Okay. Here is a function. It is y equals x squared. So what is derivative? The derivative is just we zoom in. When we zoom in, the function is quite like a line, right? Even though it has many curves, when we zoom in, zoom in, zoom in, it's quite like a line. So for this line, I can just draw it like this. So this will be the tangent line right here. And what is the slope? The slope is just we go up a little bit, we go to the right a little bit. That is delta y over delta x, right? The slope is change in y over change in x. And because I'm trying to zoom in as much as I can, that delta is a very small change in y and very small change in x. So I'm just going to call the slope dy over dx. Okay. And you can see that we can have a slope at each point, right? We can have a slope right here, which is 0. We have a slope right here, which is negative. So we can have a slope at each point. So we can take, so if this function is y equals x, we're going to take the derivative of it. And if you've learned AP calculus, it is just y equals 2x. So that means that at every x, we have a derivative. We have a slope. And that makes sense, right? We zoom in at every point and we can draw a different slope. Okay. Now let's increase the number of dimensions. So let's say we have a three-dimensional space, x, y, z. And let's say we have a surface like this. So let's say we make the x constant, right? Then when we look at this z, we imagine like slicing it on that x. Then the curve might look like that along the surface, right? And if we keep the y constant at any y, let's say, you can also imagine slicing it. Then it might look like this. So for each, I'm just gonna make the x constant, and I can take the derivative according to y, right? And if I make the y constant, I can take a derivative according to x, just like how we did this up here. Like this is just a curve. And here you can see it's also just a curve. Okay, so let's give a simple example. And if you know how to take derivatives, like in AP calculus, so right here, let's say we have a function z is x squared plus y squared. Then the derivative if I just keep x constant is just 2y. The derivative if I just keep y constant is 2x, right? So what I will do is turn this into a big vector, put 2x right here, put 2y right here. And I'll call that the gradient of f. That's it. So it's just, we take the partial derivative. Partial derivative just means making other variables constant. We take the derivative for each variable, making others constant, and then we store them in the vector right here. Okay, that's very simple to understand. So now, let me give another intuition. So right here, let's go back to two-dimensional. And let's say we have a curve like this. At this point, the slope is like this. It is positive. So which direction, and right now my x right here, which direction should I go to increase f? I should go over here, right? Which direction should I go to decrease f? I should go over here. Okay, and you can see that the slope is positive. And right now my x, I don't care what this x right here is. But when we go to the right, does that mean that means that I'm adding a positive number, right? Going left means I'm subtracting a positive number or I'm adding a negative number. Right here, the slope is negative. Right here, here's my x. To increase the function, I need to go left. To decrease the function, I need to go right. So can you see that for each point, to increase the x, I can update x by adding something times the slope, right? Like right here, the slope is negative. So to increase the function, to increase the y value, I need to move left. So the slope is negative, I need to move left. That's great. Because right here, I'm just going to be adding a negative number, and that means moving left. So that's the intuition of like going up along a curve or going down along a curve in two-dimensional space. But in three-dimensional space, it is a little bit more complicated. And in three-dimensional space, we can look at each dimension separately again. So along here, so let's say we are right now at this point, and the corresponding point on the curve is right here. So which direction should I go to decrease the z? Well, on the x, I might go over here a little bit. On the y, I might go here a little bit. And in the end, I have moved like this. Vector addition, right? But how do I know which direction is the best to move in? And I already have, so below here, I already have established that we can just times the little factor alpha. But what should the relative alphas be? For example, I might move like this, and in the end, I move like this. But what if I move a lot and a little over here? Then in the end, I move like this. They still might be like in the general same direction, but the relative alphas, they define the final movement direction, right? So basically, right here, right there, right here. Let's say we can move in any direction. Which direction will take us to increase the z the most or decrease the z the most? If we have time, we'll talk about this proof, but right now it seems like we do not have much time. So this proof, uh, if we have time, I'll go through it, but right now we won't. So this proof shows that the gradient vector, like I've defined right here, will give us exactly the direction to move in to increase z the most. And the proof above will also show that the negative direction, and we know vectors like this, right? The negative direction is over here. When we go against the gradient, that will decrease the z the most. So that is what this proof is showing right here. So what does this mean? Also, you can see here's a diagram. So let's say we're at PQ right here. The gradient is this green vector. It tells us we go over here to increase the z the most. You can see here, like the surface. To go along the green vector will increase the z the most. And you can also see that when we go opposite over here, we are decreasing z the most. So what does this sound like? Well, what if we compare the loss function to the f or the z right here, and we compare our parameters to the x and y here? So that basically tells us that the gradient gives the direction to minimize the loss, right? We just go against the gradient. So that is basically the gradient descent algorithm. So that's very cool. Okay. However, you need to understand that the gradient is local, like in my derivative right here, in my derivative example right here. The derivative is exactly at this point, it's very local. So what we need to do is when we make a step along the gradient will change, right? For example, in this derivative, I'm right here. If I go over here a little bit, the slope has changed. So every time the gradient has changed. So I need to make many small little steps. And each step is right here. So you can see we're making many little steps. And the alpha right here is called the learning rate. So we must do this iteratively by doing the steps, because at every point, when we move a little bit, the gradient will change. And the alpha defines how big of a jump we move every time. So if the alpha is big, then we move a lot. And then we calculate the gradient, and then we see, oh, which direction should we go now? So let me show you right here. So in this graph, in this graph right here. So if right now we're right here, and I follow the gradient, I've moved to here. And then the gradient changed maybe a little bit over here, then I will go over here. And then the gradient is now over here, then I'll go over here. So I'm just following the gradient, and then I will go to the end, the minimum right here. Okay, so this is the gradient descent algorithm. Is we iteratively take these small steps until we will reach the minimum, because each step tells us where you should go to minimize the loss function. And if we did not do this iterative approach, and we said, oh, the gradient is pointing right here, but we move super huge, then you'll just move over here maybe. You'll not go to the final hole right here. So that's why we have to take an iterative approach because at each point the gradient changes. Okay, and another thing is uh just from right here, you can see that if our initial point is right here, we might end up here. But if our initial point is maybe somewhere here, we might end up in another minimum. And that minimum is not as that's only a local minimum. This is the global minimum. So the initialization of our parameters matters. It's not just, oh, if you have anywhere, I promise I will definitely go into the hole. And why is it like that? Because when you go into this hole, you cannot come out anymore. Because I'm always trying to decrease. I'm always trying to decrease. So that's why you might get trapped into a hole. Okay. We'll talk about uh how to avoid the trapping later. So now let's go through the gradient of linear regression. And right now there's not a lot of time, so I'm not gonna derive it fully. So if you know AP calculus, you can derive this yourself. So, but first, for linear regression, we are trying to have a line of best fit. And we have all of these, you can see that we're trying to minimize the residual, right? Because in MSE, like right here, we're just trying to minimize y minus the prediction. So we're just trying to minimize this. We're trying to minimize this. So we're trying to minimize the sum of the squared loss. That's exactly what linear regression is. Okay, so I'm just gonna briefly go through this. If you know calculus, you can do this yourself. So we originally up here we said we said the predicted y is theta transpose times x. We said up here, right? So let's just substitute that. Let's substitute that to here. Then let's take the derivative, partial derivative, with respect to each individual theta I. And that I will not be showing here because we're kind of running out of time, but that will be like this. So this step, if you have not learned AP Calculus, then you'll not know. But if you have learned AP Calculus, you can try this yourself. Then I just put the negative into here, so it's now just like that. And then you can notice that this, what is this? This is exactly y hat. So the gradient turns out to be this. So this is the partial derivative. And this is just a number. This is just a scalar, right? We're summing over a scalar times a scalar. This is just a scalar. And previously we said the gradient, the definition is like this. We store in a vector. So, okay, let me show this. So, right here, this y, oh, okay, my pen is not working. Okay, so this y hat minus y, if I use a vector to represent that, that will be this, this is this y hat minus y. And this is the 0th, first, and nth sample. So this is a vector. And then here, the transpose. So the transpose means just taking a matrix and flipping it around. So the big matrix, the big X transpose, X bar transpose, will just be like this. So this is X0. This is X0, 0. And then this is X0, 1. And then this is X0, 2. And then this is X1, 0. And this is X1, 1. And this is X1, 2. So you can see that matrix multiplication, that's exactly this times this, plus this times this, plus this times this. And the next row is this times this, plus this times this, plus this times this. So that's exactly so that's exactly this, right? So we have written, so that's how we can write, that's how we can put all of these into a vector. So that's basically this formula. And then above, we said y hat is this. So we just substitute it in. So that is it. That is how we update our parameters theta in linear regression. Okay, now let's briefly talk about the learning rate. So I said learning rate is the step, right? So here you can see the learning rate is very small. And what's bad about it? Well, you're guaranteed to reach the minimum, but it'll take too many steps. So that is bad. Here is just right. Maybe in 100 iterations, and I'll talk about epochs, it's called epochs. So in 100 epochs, we'll be done. So that's really good. But what if it is too high? So right here, the slope is negative. I mean, the slope is positive right here. So for gradient descent, I want to move to the left. But what if I move to the left so much so that, look, this x right here, I moved it so much to the left, I moved it all the way over here. And what is the value? Value is now this. And then here, the slope is now negative. So I need to move back. I need to move to the right. But because my learning rate is so huge, I move huge. So I move back to right here. And now the slope is right here. So you can see that when the learning rate is super high, we're like diverging because we're moving so much each step. So that's also bad. So we must have the right learning rate. Okay. And finally, before we take a break, let's talk about batching very quickly. So for batching, all it is so here is the uh okay, here is the training X, right? All it is we batch the X into B batches and we update it. So regularly we have each iteration is called an epoch. And this is the same formula as above. We just update it. But in batching, we split it into groups. We split it into B batches, B groups, like this. So then we just use sum of the X to perform this gradient descent. And we do this, so let's say the whole X like this. So here's a batch, and each batch is the same size. So this is all the batches. So we just run gradient descent on this batch, then go to the next one, then go to the next one, then go to the next one. In each iteration, we do that because we got to look at all of the X, we have to look at all of the data. So what does this do? Well, first of all, this can speed up training because each time when I do you can see that I'm doing matrix multiplication here. Well, matrix multiplication can be sped up very easily if you just decrease the number of values. So that's why for each, I'm only taking some values. So that's why it'll speed up. But the bad thing about it is it'll definitely lead to noisier gradients because I'm only adjusting my theta right here based on a few samples at a time, based on B samples at a time. So my gradient is not representative of the whole thing. So each step might be very wonky like this. But in the end, I will still go into the right direction because I am using I'm going over all batches. So that should make sense. So each batch, because I'm only using some, that's not representative. So that might be very wonky. But in the end, the full direction is still correct because I'm using all batches. Okay. A special case is called stochastic gradient descent, and that is just the batch size is 1, which means that uh like I'm just looking at every sample, only one sample upgrade the gradient. Only one sample update the gradient. And then so you can see that it's super wonky, but still, in the end, the direction is the same. Okay, so we do not have a question. We do not have time to look at this question, so I'll just answer it. So, what is a way? So you can see, but however, right here, it's very wonky. What behavior does that look like? That looks like this behavior, right? This behavior right here. It's very wonky. So I'm not guaranteed. So we will go in the right direction, But I do not guarantee that exactly at this hole, I might just be like bouncing around like that because each step is still very wonky. So although I'm going the right direction, I cannot guarantee that at the hole, at the minimum, I can just I can just converge like this. I can just converge. So what should we do? Well, it looks exactly like as if we had a too big of a learning rate, of a learning step size, right? So what we will do is simply decrease the learning rate as we go, as the number of epochs increases. That's it. So then we will solve the problem of right here, it being too wonky right here. And then we will converge successfully. Okay, so now let us take a 1 minute break because we're kind of running out of time. Let's take a 1 minute break. Actually, 2 minutes, 2 minutes, 2 minute break. Okay, and I will put this on. So please join the Slack if you have not. And maybe in the end, if we have time, we'll talk about the final showcase stuff. But I will also send out a registration form today, and you can read the rules yourself. But maybe in the end, I'll talk about this. So yeah, so just right now, please join the Slack. Okay, let's take a break. Okay, let us get going again. And I'm going to be teaching for the second half. Okay. So a little recap of what we already have done. So of course, we have gone through supervised, semi-supervised, and unsupervised learning. So unsupervised means there is no y, right? There is no ground truth value. But semi-supervised means some have the ground truth, some do not. Like maybe a 5% or 95% split. But supervised is what we're focusing on today. And every sample has a y that we want to predict. When that y is continuous, we can use linear regression, as Victor already talked about. And linear regression is one of the simplest forms of continuous supervised learning. But now let's talk a little bit about categorical supervised learning. And that is classification, because we want to classify if a data point is in class A or class B. So the y, it is not a number. It's not 0, 1, 2, 1.5. It's not like that. It is like red or blue, or male or female, or if this email is spam or not. So that is classification. And that y is discrete, means it has limited number of values. And a little subset of that is binary classification, which means that y is in 0 or 1. And how do we evaluate that? So, okay, I can classify if this data point is 0 or 1. But how do I make sure that my model is good? What is the loss function? Well, let's first start with our evaluation metrics. So first we have accuracy, which we all know, right? If a test, if I get 9 out of 10 correct, then my accuracy is 90%. And right here, the notation is a little bit big, but it's very easy to understand. Here is the ground truth values, and here are the predicted values. And predicted is marked by a hat, as we have already seen. And this just means, of course, all the samples from 0 to big M minus 1. And here is averaging. So we add all of them up, and then we divide it by n. That's averaging. And this is called the indicator function. So this plus is 1 when the ground truth and the predicted class are the same. Which makes sense, right? If accuracy, we want to count how many are correct divided by total. So total is n. How many are correct is this. And of course, we know that accuracy is between 0 and 1. However, accuracy may not always be the best metric, and we will explain that later. Next, there is a metric called precision. And precision, of course, you take in all the predictions and the ground truths, and it's like this. TP and FP. What does TP mean? Well, TP is true positive, and FP is false positive, and TN is true negative, FN is false negative. True means that I predicted correctly, and positive means I predicted positive. So true positive means I predicted positive and actually it was positive. And false positive means I predicted positive, but I predicted wrong, and actually it is negative. So precision, the denominator is true positive plus false positive. What does that mean? That means out of everything that I predicted that is positive, how many did I get correct? And similarly, we can have recall. But the denominator has changed. It is true positive plus false negative. Well, what is false negative? False negative is I predicted negative, but actually it is positive. So denominator means out of the actual things that are positive, so out of all the ground truth positives, how much did I predict correct? And they're different. They're not like precision is not better than recall, recall is not better than precision. So these two are also some metrics, and precision and recall is important to know that these are for a class. So we can have precision for the positive class and precision for the negative class if we're doing binary classification. And also the same as recall, recall for the positive class and recall for the negative class. And there's another metric called F1 score, which combines precision and recall. And this is called a harmonic mean. And harmonic mean just balances it so that if one of them is bad, F1 score is bad because we want both precision and recall, right? Precision is out of all the things I predicted, how many are correct? And recall is out of how many are correct, how many did I predict they are correct? So we want both of them to be very high. Well, you might ask, when are they not going to be high? And how is accuracy a bad metric? It seems very straightforward, right? However, if we look here, here is a confusion matrix, and here is what I just described as the true positive and true negative, and false positive and false negative. Here are the actual values or the ground truth. Here are the predicted values. And you can see precision and recall. But I'm going to give you an example of why accuracy may not be the best metric. So let's just say that 5% of a population has a disease. And there are 1,000 people in total. Okay? And I have a medical test to test if I have a disease or not. So I can draw a confusion matrix after I ran the test on all of the 1,000 people. So here are the actual values, positive or negative. So this means a person actually has the disease or does not have the disease. And here's predicted, which is what my test predicted. So 5% of 1,000 is 50, right? So in total, there are 50 people who have the disease and 950 who don't. So let's just say out of the 50 people who have the disease, I predict 45 and 5, which means out of the 50 people who have the disease, 45 of them, the test predicted, yes, they do have the disease. And 5 of them, the test predicted wrongly. And now for the people who do not have the disease, let's just say the test predicted correctly 900 times and wrong 50 times. So here is a confusion matrix of my test. So what is the accuracy of my test? Well, accuracy is correct overall, right? So correct is 45 and 900 over all, which is 1,000. So that means my accuracy is 0.945. Sorry, is 0.945, which is pretty good. You might think that's pretty good. However, let's look at precision. And what was precision again? Precision is out of every one that my test predicted positive, how many of them are actually positive? So it is this 45 divided by 45 plus 50. So it's 45 divided by 95. So my precision is just 47.4%. What does this mean? That means if I administer a test to somebody, there's only a 47.4% chance they actually have the disease. So is this test even useful if I give the test to someone and it's not even 50% sure the person has the disease? So that's why you can see that accuracy is a little bit misleading. And the real medical fact in the real world is that most tests are like this because we do not want false negatives, because false negative means they have the disease, but the test does not show that. That means we are denying a sick person treatment, which we do not want. While here is also a wrong prediction, but this means I do not have the disease, but I predicted positive. That means I'm giving me a healthy person some unnecessary treatment. And from a medical standpoint, reducing this is more important. But if we put more emphasis on this, that might mean that the precision decreases, which is not good for tests. So that's just something to keep track of. So accuracy, it is not the best metric. So what should you be using when the classes are super imbalanced, such as this one? Only 5% are of one class and the other 95% of those is of the other. Well, you should be using the F1 score as shown here. And for this case, the F1 score is around 0.621, which means that it is not the best test, which is a pretty accurate representation of it, as opposed to accuracy, which says 94.5%, and that's not a very good, a very holistic view. So let's now move on to the loss function, because of course we know that if we want to train a model, we have to minimize the loss. So what is the loss for our function? Well, first of all, let's see what the function even does. So logistic regression is what we're doing. Logistic regression, it is just a linear regression and then a sigmoid afterwards. What is a sigmoid? Let's find a place to write this. Okay. So linear regression, of course, we know that. Oh, okay. Sorry. Linear regression is theta t times x, right? So this is for one sample. I have all the features. So this is d by 1. And theta is our weights, and it is 1 by d because it is transposed. Okay. So this one is the result for linear regression. But this is a number. We do not want to have a number. We want to have a class. So what do? We wrap this around a sigmoid. And what this does is sigmoid, it looks like this. So this is the x-axis, and this is the y-axis. So if y equals the sigmoid of x, then it will look like this. And it pushes an asymptote. So right here, the value is 1, and right here is 0. And here is the middle with 0.5. And this is a pretty convenient way, right? Because if my linear regression, if my here, if that predicts above 0, then if I input it into the sigmoid, then my sigmoid is going to be above 0.5. And we can treat 0.5 as a confidence score to say, okay, if we predict 0, if the linear regression predicts 0, we're not very sure. So it's 50-50. But the more positive my linear regression predicts, that means my confidence is going to be higher, 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 all the way to 1. So sigmoid basically is a confidence score, and this is the here is y prediction. And from here we can determine the class, right? For binary classification, if this is greater than 0.5, then it is class the positive class. And if this is less than 0.5, it is the negative class. Okay. Now, let's see the loss function. So this loss function, it might look kind of nonsensical right now, but it is very intuitive. This just means average over all the samples. Here means for every class. And here is another example of the indicator function. It is 1 when yn equals c. And yn, right? This is y prediction. This is the y prediction. This is what we predict. And yn without the hat means the ground truth. So when the ground truth is class C, we activate this, and this log, what is this? This measures how off it is from class C. Because yn, when yn is close to 1, that means it's very confident, right? And what is log of 1? Log of 1 is exactly 0. But when yn is not very confident, so if yn is about 0, the model did not even think of predicting this class. If the prediction, this is 0, well, what is log of 0? It's negative infinity. So negative infinity times this negative sign right here, that means it's positive infinity. So when y is very confidently correct, this is 0. When y is very confidently wrong, it is negative infinity. Or if we have this negative sign, positive infinity, which is a very good value for our loss function, right? Because if it is confidently correct, it is 0, which is a very small number, and it does not add to the loss. But if it is confidently incorrect, well, we really do not want that, right? We want to correct that. So we make it to be positive infinity or close positive infinity. so that the loss function is a lot. And as you can see here, here is a subcase of cross entropy, which is called binary cross entropy. And because we are talking about binary classification, there are two classes, right? If I predict a probability for the first class, then naturally the probability for the second class is 1 minus the probability of the first class. So here is probability of the first class. Here is probability of the second class. And it is very intuitive, right? If it's either this or that class. So we do not need to predict two things. We only need to predict one thing, which is y hat. And y hat is what again? Y hat is the sigmoid of my linear regression in here. So this is a graph representation of binary cross entropy. If my y is 0, so if my ground truth is 0, and I predict p of y is 1, that means I predict very confidently it is not this class. Well, that's not very good, right? We want the loss to be very much, because that is very wrong. But if my class is 1, and I predict yes, I'm confident that it is class 1, well, that's very good. So my binary cross entropy is 0. As you can see, this is a very intuitive and very functional loss function for classification. And as you can see, the threshold is 0.5 because the sigmoid function looks like this. And this is just 0.5, so that we can say the linear is 0, more than 0, or less than 0. Okay, so that is the essence of logistic regression. And we see that every sample is xn, right? Xn, and this n means the n sample. And this has all the features. And I believe we have seen this already when Victor was talking. So here is the feature matrix, which we have also seen when Victor was talking, right? This is n by d. Every row is a new sample, and each column is a feature of the sample. And of course, here is we're just doing linear regression, nothing new, because logistic regression is just a linear regression plus a sigmoid. And then the weights is also nothing new. Yeah. This we append one, yeah. So this gives us this, which we have already seen before. And the ground truth, though, this ground truth is a little bit interesting because this is not R. Oh, okay, this is not. Oh, this is not R of n anymore because our y, it is not continuous. We're not trying to predict the value of a house or somebody's age or something like that. We're not trying to do that. We're trying to predict if it's either 0 or 1. That is binary classification. So it's either 0 or 1 of n. So this first one might be 0, the second one might be 1, this last one might be 0. It's like that. And as I've written before, logistic regression, the whole equation looks like this. We have a linear regression in here, and then we have the sigmoid out here to make it into a classification task. And then if we write it as a big matrix multiplication, it is like this. And the sigmoid function, I've drawn it before, right? It looks like this. But what is the actual formula? It is this one. And this one, well, why is this one so special? There's a specific reason. Because the logistic, the sigmoid derivative, the sigmoid derivative, it is because we are trying to do gradient descent, right? And gradient descent requires you to take the gradient. So we have a loss, right? The loss is the binary cross entropy. And this takes in the y prediction, right? The y prediction and the real y. And this y prediction is sigmoid of theta t times x n. And this, of course, if we want to take the gradient of the loss, if we want to take the gradient of the loss, then we also need to take the gradient of this. And if you have learned calculus, we'll need to do chain rule to go in and in more and in more and in more to find the whole gradient. So we choose sigmoid because, first of all, it looks good, right? We have 0.5, it is naturally like a confidence score. But also because its derivative is very good. The derivative, okay, the derivative is itself times 1 minus itself. And if you know calculus, you can derive that on your own. It is quite easy, actually. Just need to know that sigmoid is 1 over 1 plus e to the negative z. So, of course, right now we have trained a model, but we want to see what the model is doing. Well, right here can be a sample logistic regression model. But of course, logistic regression, it is not linear regression. And linear regression, it is using x1 and x2 and all of the x's to predict the y. But currently, our y cannot be displayed on the axis. Our y is either 0 or 1. So our y is displayed as the color. If y is 1, that means it's red. And if y is y is 0, that is displayed as blue. And here both axes are x's. And what does this line represent? This line is not the same line as the linear regression line of best fit. Because that line, the y-axis is actually y, and you're trying to have a relationship between x and y. But no, we're not doing that. For this line is called a decision boundary. And a more technical term is a hyperplane. But we don't need to worry about that right now. This decision boundary occurs when theta t of xn equals 0. Because to the left of this line, it will be either greater or less than 0. And to the right of the line, it will be the opposite. So to the left of this line, we predict everyone should be class 1. And to the right of this line, we predict that everyone should be class 0. And as you can see, it's not a 100% accuracy. Because as you can see, this side is supposed to be y equals 1. But right here, we have let y equals 0 in. And over here, it's supposed to be y equals 0. But you can see we've let a y equals 1 in. So of course we all know that the data is always going to be a little bit noisy. It might not be possible to separate it all fully. But that is why we're trying to train a model to find the best model to separate these points. And as you can see, here's the BCE loss, right? And this is loss. So as Victor said before, if we want to do gradient descent, we need to minus the learning rate times the gradient of the loss. So of course we can calculate the gradient with these, and then after many steps, I'm just not gonna write it out now because it is very time consuming and very complicated. But the essence is it becomes like this. And as you can see here, this very much is very similar to the linear regression gradient, right? What was the linear regression gradient? The linear regression gradient was 1 over n times xt, and the linear regression gradient was x theta minus y. So we can see that everything is the same except for here. And it makes sense, right? Because here, linear regression is trying to predict y directly with this matrix multiplication. But of course, logistic regression, we need to wrap it in sigmoid so that it becomes a confidence score, and this y is either 0 or 1. But as you can see, through all of this uh, derivative stuff, we get the same thing. So we can see how linear regression and logistic regression are similar and are connected, and that is why we use sigmoid even in the first place uh, 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 because sigmoid is the only activation function that makes it to be the same for logistic and linear. And that is very beautiful. That's what we want. So of course, the gradient descent function becomes like this. Here's the learning rate. Here is the gradient, and we want to move in the direction to decrease the gradient. Okay, so that marks the end of our class for today. So let's do a quick recap. So first of all, we talked about supervised, unsupervised, and semi-supervised. Recall that supervised means there is a y and we're trying to predict it, and the loss is that as well. For example, mean squared error, as Victor has said, that is the average mean squared residual between the ground truth and the predicted, right? Unsupervised means there's not really a y. For example, clustering. I want to make the y. I want to separate this into clusters, into this cluster and that cluster. So there is inherently not a y. And unsupervised, we have not talked about today. Linear regression and logistic regression, those are all part of supervised learning because we're all trying to predict a y, right? For linear regression, that y is a continuous number, for example, housing cost. And for logistic regression, that y is a category. It's either 0 or 1. And for semi-supervised learning, we also have not talked about that, but we just need to know that for in real life situations, it is not it is very often the case that not all your data is going to be annotated. You might because it might be very labor intensive, but even if it's like that, we can find solutions to use all of that data effectively and train a good model. And then we talked about gradient descent for ML and DL. So why does this say some of ML and all of DL? We're not even talking about this class not even for DL. But the thing is, ML it is like DL is all based on linear regression, right? DL, like for example, neural network. What is a neural network? It is just a linear and then an activation function, and then linear and then activation function, and then linear. That is the simplest deep learning, which is called a multilayer perceptron, but we don't need to worry about that today. But this is all made of linear regressions or a linear layer. So all of DL uses the gradient descent method we have described for linear regression. But ML, it is a little bit more diverse. ML, there are things like trees, like random forest classifier. That is, I like split the data into here and here. Oh, and then the criteria, I split the data into here and here. So that is not linear regression. That is its own thing, and it has its own optimization things, and that is not gradient descent. So that we can talk about later, but today we have talked about linear regression and logistic regression. They all use gradient descent. Linear regression is the easiest machine learning regression model. And as you can see, regression and classification. Remember that regression is we're trying to predict a continuous y, and classification is we're trying to predict a categorical y. And so linear regression is the tool for regression. Logistic regression is the tool for classification. Just remember that logistic regression is you wrap linear regression in a theta. Sorry, not, no, no, sorry, in a sigma. Okay, that concludes the end of the first class. We went a little bit over, but I think that is fine, especially with the introduction. So if right now, if you have any questions, please ask the chat, and we'll also talk a little bit about the competition. Okay, so for the competition, let us briefly look at the. So here's a Google form. I'll send it out through email and Slack. And here's the competition rule document. So let's look at it briefly. So, it's just a presentation competition. You will use what you've learned in our 3-day class to solve a real-world problem. It is next Saturday and Sunday. So it's not this Saturday, Sunday, it's next. And the registration deadline is August 11th. You can be individual or team of 2 to 4 people, and if you know other friends, you can also invite them. Or if you want to join a team with other friends. If you don't know how to form a team, you can go to our Slack right here. You can go to our Slack and contact people. So that's why I said please rename yourself with your real name so that people can contact you. Okay. You can also ask us for help. For teams, please only let one team member fill out the form. Okay. And then we have middle school category and high school category. The middle school, but if middle schoolers team up with high schoolers, then that will have to be high school to ensure fairness. Okay. And after August 11, we'll send out Google Sheets with everyone's competition time. So yeah, and if it does not work, you can email us. And the best thing is in total we'll have about $500 for prizes in total. So we're still figuring out like first prize is how much and how many second prizes, how many third prizes. But for now, you can know that it's 500. So that's a lot of money. So please participate. Okay. So here is our rules. So uh we 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 talked about machine learning. So right now we have not talked about Google Colab. We'll do that in the next 2 days. But Google Colab, you'll just need to submit a Google Colab notebook that shows code and results. For example, tables and graphs. That's it. And then for the presentation, you can just scroll down and talk about everything. That's it. You don't need to submit. So it's a presentation competition. And the topic can be anything like biology, medicine, physics, whatever. And the type of problem, like today we've discussed regression and classification. If you want to do time series prediction, like for economics, like if this store, what's the profit tomorrow? That's also great. But please do not use deep learning because first of all, if some of you know deep learning, you know that deep learning is super powerful. It is much harder to train and it may require GPU and all of that, but uh, please do not have that because you might get like a huge F1 score. So that's not really fair. Okay. And here's a simple rubric. You can look at this yourself. We'll send out everything later by email and by Slack. So you can look at this yourself. And then each team will have around 5 minutes to present and 2 minutes for judging, making the total time 7 minutes. And finally, if you want to use AI tools, that's encouraged, that's allowed. You can let AI like write code, that's fine. But please do not let that prevent you from presenting. And we will know if you like present confidently or not. Yeah, we will ask you questions to see if you actually know what you coded and if you know the material. Okay. And some competition advice is uh some competition advice is Kaggle is the best machine learning dataset. Yeah, like database. It is free and is fully downloadable. You'll find all sorts of data there. So Kaggle, just go to kaggle.com. Another is the UC Irvine Machine Learning Repository. It's a little bit more formal, but still. There are very cool datasets, and it has very standard and famous datasets like the Iris dataset. Finally, you can also ask AI for like datasets online if you for like your specific problem. Okay, and do not today we discussed like F1 score and MSE as evaluation metrics. Please do not be discouraged if you do not get a huge F1 score or like accuracy. We'll look at your whole data preprocessing phase and model selection phase and all of that. So if you get like 0. And in fact, like if you get 0.7 or 0.8 already, you're already super solid. Like in medical, uh, in the medical field, there's no way you'll get 100% accuracy. There's not even a way that you'll get 90% accuracy. So yeah, do not be discouraged. We'll look at everything. Thank you. So that's it. Okay. And then a final note. So today, if today's notes might have been a little bit complicated and a little bit math heavy, but next time's notes will definitely be less math heavy. It will be more like other machine learning topics, and I've already sent out the second note so you can take a look. So yeah, but today, so let me quickly recap. So because our class has ranging from seventh graders to 12th graders, it is of huge variety. So we want to provide as much information as possible. So if you are in middle school, that's fine. These notes are just like introduction. If you do not understand all of the derivations, that's fine. For 12th graders or 11th graders or 10th graders, if you have learned AP calculus, we highly recommend you to like take the derivative. It's very easy. The derivative of log is just one log of natural log of x, derivative just 1 over x. So you can derive our formula right here very easily. We've just provided you with it. So if you've learned AP calculus, that should be easy. But if you have not learned AP calculus, for example, if you're middle school, then at least you can understand that, for example, gradient descent provides a way to go down the loss function, and that is the heart of machine learning and basically deep learning, like backpropagation in deep learning. So yeah. And finally, one last thing is if you have any questions, for example, regarding these notes or competition or anything, feel free to ask in the email or Slack.
Yeah, we have already responded to many questions and we will respond as soon as possible, especially because we're right now not in school. We have all of day to monitor if you have any questions. And if you have any questions right now, you can ask it in the chat. We have sent out everything, for example, the notes and the competition rules. We'll send that out very soon. So everything is available. If you have any questions, you can ask us or you can ask ChatGPT, but make sure that you understand what you're doing because for uh everything in life, you cannot just let AI do it for you. You have to understand. You have to use AI as a tool and not a replacement. So thank you. And if you have any questions, please ask. If not, then we can end it here.
Yeah, you're free to go. Somebody said, will you guys share the competition details Google Doc? Yes, I will send it all. I'll send it out after the class.
Yeah, through email and the Slack. And if you have not joined the Slack, please join so that you can
Yeah, please everybody join the Slack.
Yeah, because Slack is you can find our notes very easily and you also message other people if you want to team up them or yeah.
All right. Thank you.
We will stay on if you have any questions, but you're free to leave.
Yeah, we'll stay on for a few minutes. Okay, so somebody asked, what would machine learning look like compared to deep learning for a competition? So I just said we cannot really use deep learning. Deep learning is not allowed. Please do not use deep learning. But so machine learning, traditional machine learning is tabular data, like what we discussed today. Like the X is, for example, income or housing prices, and you're trying to predict the house, like the household value or something like that. That is tabular data. But deep learning, there's many modes. For example, image, classify an image. Classify if this is dog or cat, or classify this audio. Or, for example, transformers, they are for language understanding. So that is very complex. Uh, like this workshop is focusing on traditional machine learning, but if later we can also try to do another full workshop on deep learning, but that'll be very complicated. So right now, please do not use deep learning if you know how to use it, because deep learning is fully capable of solving, for example, machine learning problems. It is fully capable of solving tabular data. And if you learn later on, there is something called the universal approximation theorem. It says that if you have just enough layers or enough neurons, you can approximate any function. So neural networks are super powerful. Uh, so that's why we do not want you to have deep learning for the competition.
Yeah, we want you to try and use machine learning methods in innovative ways. And if you're unsure of, oh, is this machine learning or not, you can
Ask us.
yeah, you can ask us or you can ask ChatGPT or yeah. But yeah, please use machine learning methods. You can use any pre-processing or any like data set, anything, but please try to use an innovative machine learning method to solve a real world problem. That is what we want for the competition.
Yeah, and right now we've not even talked about Google Code Lab. We'll talk about that in the next two classes so you'll get a better understanding of what like a notebook is and what training a machine learning model looks like. Okay.
Okay, if you have any other questions, please ask. You can do it via email or Slack, but we're going to end it here. Thank you all for listening to our lecture, and remember to come back tomorrow.
Yeah, and have fun.
Thank you.
Okay, let me stop sharing.